All right, so in this video, we're going to identify the best fitting model for a real-world set of data. So there's really four models we're going to focus on. The first one is a quadratic function. Let's just talk about some application problems that could potentially use a quadratic model. So really anything that involves projectile motion, which means throwing something in the air and then gravity taking effect and it eventually landing. So any type of problem that deals with rockets or someone throwing an object in the air. But again, this will differ. It's all about the data points. And in real world data, you're never going to see data that models a perfect U-shaped graph, but it's going to be a scatter plot. And they're going to kind of have that quadratic pattern to them. Next example, logarithmic function. So one example that I see this a lot of times is the height of a person over time. So we know that over time, most people tend to increase at a rapid rate at a certain age, but at a certain point that kind of flattens out. But again, everybody's a little bit different. You'll have some people that are way up here, and you have some people that are much further down. But in general, everybody's height eventually flattens out and kind of has that logarithmic shape to it. Exponential functions, you've seen that in the news a lot, obviously. Or even money. Think compound interest. Again, an exponential function is something that most of the time when we're doing application problems, not always, but we think of an exponential increase. But we, of course, know it cannot also go the opposite direction. And the final type, of course, is a linear function. There's any example where the rate is constant and doesn't let up. So there's a lot of steps in the calculator we're going to go through with these problems. You'll see in a second. But basically, these problems boil down to four steps. First, you make a scatter plot of the data, kind of like we did up there, except we were just making up the data points. Step two is going to be your first mathematical step. You're going to visually evaluate the scatter plot to determine the best fitting model suggested by the data. This step can sometimes be difficult because sometimes it looks like multiple models may work for a data set. So when you're initially doing this, you want to use logical thinking about what the problem is talking about. So for instance, if we are talking about a person's height, you could say there's a certain point of a person's height where it is increasing at a linear rate. But if you stretch that out over the course of their lifetime, that's a logarithmic function because eventually it does flatten out. So visually evaluating is important, but we're going to use the graphing calculator to kind of check that visual evaluation. I'll show you how in just a second. Step three is we're going to find a model using our graphing calculator. And again, we're going to focus on these four models right here. This is how they appear in the graphing calculator. They use a lot of A's and B's, which is a little bit different than what you probably first saw when these concepts were introduced to you. And then finally, we're going to use a combination of logical thinking and something called the correlation coefficient that the graphing calculator will provide to determine if the model you chose is the best fitting model. A solid model will have a correlation coefficient that's approximately 1. So after you do the visual step where you determine your model, you want to look at your correlation coefficient that the calculator provides. And if it's not approximately 1, it's obviously not going to be exactly 1. If it's in the ballpark, and that means the model you chose is probably a strong one. So let's look at one example here dealing with real estate. So they give us data for the years since 1950 and the corresponding cost of homes, the median cost of a home in thousands of dollars. And one thing I'm going to slightly correct about this table, in the first row it says years since 1900. So instead of writing 1950, I'm going to write in 50 because the number 50 represents 50 years after 1900. And likewise, 60 is talking about 1960, and so on and so forth. This happens a lot with the X variable where we have to kind of scale down the number to make the math calculations of the graphing calculator a little more possible. The bottom row is fine, but just keep in mind that 7.3 is talking about $7,300. And 221.8 is $221,800, since we're talking about cost of a home in the thousands of dollars. So now I'm going to fill out my scatter plot, and the y-axis is, of course, the cost in thousands of dollars. And so our lowest cost is 7.3 and our highest is 221. So I see the range of these numbers. If you subtract those two numbers, 221 minus 7, you get about 214. And there are 10 tick marks across here. So if you divide 214 by 10, you get a number that's right around 20. So I'm going to count by 20 on the y-axis. And you'll see we're going to go off the grid just a little bit, but that's okay. And then our x-axis is the years since 1900. And again, our range, our lowest number is 50, highest number is 110. So if you take the difference is 60, and you take 60 and you divide it by 10 tick marks, that's about 6. So you can count by 6. I think that's what I'll do. So 1950, 1956, 1962. And then finally, we're going to make our scatter plot. So my first ordered pair is the point 7.3, comma 50. My second ordered pair is 11.9 and 60. And again, these are just estimates. We're not going to be able to hit them right on the dot. You can see especially these first 3 points are tough to graph because they're all kind of in that 0 to 20 range on the cost. So we've got all our points graphed. And again, we can see these first 3 points are really kind of bunched up. There's not much of an increase there, but it looks like the increase is getting bigger and bigger and bigger. So to me, this lends itself to an exponential function. We're increasing at a faster and faster rate. So I'm going to go with exponential when I do this problem. All right, then we're going to input the data in the calculator. So these steps are online in paper format, but we're going to hit Stat Edit. We're going to make sure there are no items in L1, and then we're going to enter all of the X values in L1. Starting with 50, type it in, hit Enter, and work your way down. Every time you type in an x value, hit enter until you get all the x values in L1. All right, so all my x values are in there. Then I'm going to go to L2 and do the same thing and type in my y values. Just make sure, watch for typos. It's really, really easy to make a small mistake when you type these in. So all the data points are in L1 and L2. So next we want to calculate the equation. So we're going to hit Stat, scroll to the right to calculate, and we're going to scroll all the way down until we find exponential regression. We're going to hit the number 0, hit enter, and really just keep hitting enter until it calculates the equation for you. I'm going to round this to 3 decimal places when I write it out. So the A value is 0.364 times the B value of 1.060 raised to the x power. One thing we did not do, we didn't get our correlation coefficient. So real quickly, if you press the mode button, and we want to turn our stat diagnostics on. And now we're going to do the stat calculate and then choose the exponential regression function. And then this should give us a correlation coefficient. Again, we're looking for something close to a 1. You can see we're right in the ballpark there of 1. So this looks like it's a pretty solid model. So now what we can do, it says according to the model equation, what was the median home cost in 1975? So since our x variables were the years, we can just substitute 75 in for x. And of course use a calculator to evaluate that. So 0.364 times 1.06 raised to the 75th power. And that gives us 28.77. And if you look at the graph, the year 1975 would be somewhere right around here. And if we go up to our curve, do we find 28 in that? Pretty darn close. So you can see this point on the curve is directly above the year 1975, and it's right around the value that the calculator is providing for us. So according to the model equation, what was the median cost of a home in 1975? The median cost of a home was $28,777. And do the same thing for the year 2020, except obviously we're going to plug in 120 for x. So type over that 75, put in 120. Should be a pretty big number. Yeah, 396,000 and $100. That's the median price of a home in 1975.